You know that feeling when you're inside, the AC's running, but you still feel just kind of sticky, uncomfortable?
Oh, yeah. Or that room that just feels stuffy no matter how much you try to cool it.
Exactly. It really makes you wonder, what's actually going on with our indoor air? And what does it really take to feel, properly comfortable?
It does. We tend to just fiddle with the thermostat, right?
Yeah.
But when you look at the actual engineering behind air conditioning, you see there's so much more to indoor comfort than just temperature.
Absolutely. And that's exactly what we're diving into today. We've got some really fascinating material here. Everything from the surprising history of AC to the deep science of managing humidity. We want to figure out that real recipe for a comfortable indoor environment.
And it's so important when you think about the energy involved. I mean, take Hong Kong, for instance. It's pretty staggering. 32% of their total electricity use goes to air conditioning.
Wow, 32%.
Yeah. And it gets even higher in non-domestic buildings, jumps to 72%. It really shows how vital and, frankly, how complex this whole topic is.
That kind of energy use, it really puts it into perspective globally, doesn't it? It's not just personal comfort, it's a huge energy question.
Definitely. A big piece of the global energy puzzle.
Okay, so let's talk about comfort. When we say that, in terms of indoor air, what are we really talking about? It feels so subjective sometimes.
You're totally right. There's a big subjective element. Our own experiences, maybe our mood, the situation we're in. It all plays a part.
Yeah, like what feels good to me might be freezing to someone else.
Exactly. And what we're used to, that matters too. Plus, sudden changes, walking from a hot street into a cold building or how long you're in that environment. It all shifts our perception of comfort.
So it's not just a number on the thermostat, but surely there are things we can actually measure, like objective factors.
Oh, for sure. We look at several key things objectively. Temperature, obviously, but not just the air temp, also our own body temperature and the temperature of surfaces around us, like walls or windows.
Right. What else?
Then there's relative humidity. That's the big one for that sticky feeling.
Yeah.
Or conversely, really dry skin if it's too low. And indoor air quality, that's huge. We're talking contaminants, chemicals, dust, molds, bacteria.
Okay.
And just making sure there's enough fresh outdoor air coming in. Plus, you can't forget lighting natural versus artificial, and even noise levels. They all feed into that overall sense of comfort.
It's a whole package deal then. Okay, so how does our body fit into this? It's not just passively feeling the air, is it? Our body's doing stuff too.
Not at all.
Yeah.
Our skin is like a central player here.
Yeah.
You got the outer layer, the epidermis, that's the barrier.
Right.
And underneath the dermis, that's where the sweat glands are, among other things.
Sweat. Fun topic.
Yeah, but crucial. When we get warm or exercise, these glands release sweat. But the cooling magic isn't just being wet.
It's the evaporation.
Exactly. It's the sweat evaporating off our skin. That process pulls heat away from the body. It's a primary way we regulate our core temperature, trying to keep it stable around 37 degrees Celsius.
Homeostasis, right?
Precisely. And it's constantly adjusting based on our metabolism, how much energy we're burning, and our activity level. So yeah, our skin is vital for losing heat directly and through that evaporative cooling.
Fascinating. So there's an energy exchange constantly happening between us and the room.
Totally. You can actually think of our body managing its energy budget. There's even an equation for it. MW equal H plus E plus Cres plus Eris.
Whoa, okay, bring that down a little.
Okay, M is your metabolic rate, the heat you generate. W is any physical work you're doing. H is the dry heat you lose directly from your skin. E is the heat lost from sweat evaporating. And Cres and Eris, those are about heat exchange through breathing.
Okay.
The key takeaway is just that feeling comfortable isn't just about the air temperature. It's about this whole energy balance our body is constantly trying to maintain with its surroundings.
Wow. Yeah, there's so much going on under the surface. So, okay, from an engineering perspective, are there actual standards? Like what counts as comfortable?
Yes, definitely. Organizations like ASHRAE, that's the American Society of Heating, Refrigerating, and Air Conditioning Engineers, and ISO, the international standards body, they've defined thermal comfort.
Which is?
Basically, it's that condition of mind where you feel satisfied with the thermal environment. They use a metric called the predicted mean vote, or PMV.
PMV.
Yeah, it's a 7-point scale. Goes from cold, like -3, up to hot, +3. 0 is neutral. The target for comfort is generally landing somewhere between -0.5 and +0.5.
So just slightly cool to slightly warm is the sweet spot for most people.
Pretty much.
Yeah.
And calculating the PMV involves several factors.
Yeah.
Humidity, air temperature, how fast the air is moving, the radiant temperature, that's heat from surfaces.
Right, like a warm wall or a cold window.
Exactly. Plus, how much insulation your clothes provide and your metabolic rate, how active you are. So engineers use this PMV to aim for conditions where most occupants will feel comfortable.
Okay, that's quite a few variables already. Are there even more subtle things that affect comfort beyond those main PMV factors?
Oh yeah, absolutely. Your specific metabolic rate, measured in MET units, matters. And your clothing level, measured in clo units. A business suit has a higher clo value than shorts and a t-shirt, obviously.
Makes sense.
Then there are different ways of looking at temperature, not just air temp, but things like operative temperature or mean radiant temperature, which try to capture the combined effect of air and surface temperatures.
So a more holistic view of the heat around us.
Exactly. And then you get into things like airspeed too much can feel like a draft, which is uncomfortable. Or asymmetry in thermal radiation, like having a really cold window on one side and a warm wall on the other. Even the difference in air temperature between your head and your feet, or the floor temperature itself. It all plays a role.
Man, it really is a complex dance. Way more than just dialing down the thermostat. Okay, let's switch gears slightly. Air conditioning feels ubiquitous now, but it wasn't always around. Can you give us a quick history? How did we start cooling buildings?
Yeah, it's a cool story, actually. Pun intended, maybe. Back in the 19th century, Michael Faraday, the British scientist, he figured out that compressing ammonia and letting it evaporate could produce cooling.
Okay, early days.
Then, fast forward to 1842, Dr. John Gorey in Florida, he used compression to make ice, specifically to cool air for his hospital patients.
Wow, for medical reasons initially.
Yeah, but the first sort of modern electrical air conditioner, the kind we'd sort of recognize, that was invented in 1902 by Willis Haviland Carrier.
Ah, the Carrier. I knew the name.
That's the one. And his company really pushed residential AC units in the 1950s, which, completely changed architecture and how we live, especially in hot climates.
Incredible. What about the stuff inside those early machines? The refrigerants, were they the same as today?
Not quite. A big step came in 1928 with Thomas Midgley Jr. He created Freon, the first of the CFC's chlorofluorocarbons.
Freon. Heard of that too. Was it better?
Well, it was seen as much safer for people than things like ammonia or sulfur dioxide used earlier, but, and this is a big but, we later discovered CFCs were incredibly damaging to the Earth's ozone layer.
Right, the ozone hole problem.
Exactly. It's also interesting you see modern AC units now often including air sterilization features too. It's always this search for the perfect refrigerant works well. Safe for us, safe for the planet. It's a tough balance.
So Freon was a breakthrough but had this major environmental downside. Okay, that brings us to the basics. How does an AC unit actually work? What's the science of making cold air?
Okay, so at its core, refrigeration, which is what AC is, it's just about removing heat from a space or a substance, right? Making it colder than its surroundings.
Simple enough concept.
And it does this using a special fluid, the refrigerant, in a continuous cycle. This refrigerant absorbs the heat you don't want inside. And in doing so, it changes state, usually from a liquid to a gas.
Mm-hmm.
It evaporates. This makes the refrigerant itself hotter. Then, elsewhere in the system, it releases that heat and changes back into a liquid it condenses.
Okay, so it's like a heat sponge, soaking it up inside and squeezing it out outside.
That's a pretty good analogy, yeah.
Mm.
And the key principle driving it is that when a liquid expands into a gas, it absorbs heat from its surroundings. It's latent heat.
Latent heat. Hidden heat.
Kinda, yeah. It's the energy needed just to change state, not to change temperature, like melting ice or boiling water. That takes energy, even if the temperature stays the same during the change. The AC system harnesses this effect. The refrigerant is pumped around in a closed loop, constantly evaporating and condensing.
And I know there are different parts inside the unit doing specific jobs. Can you break down those main components for us?
Sure. There are basically four main players. First up, the compressor. Think of it as the heart or engine of the system.
Okay.
It takes the refrigerant, which is a low-pressure vapor at this point, and it squeezes it, compresses it. This makes it a hot, high-pressure vapor. The pipe bringing the vapor in is the suction line, and the pipe going out is the discharge line.
Got it. Compressor squeezes the gas, makes it hot and high pressure. Then what?
Then that hot, high-pressure vapor flows through the discharge line to the condenser. This is usually the coils you see on the outdoor unit.
Right, the bit with the fan blowing hot air.
Exactly. The condenser's job is to get rid of that heat. Air blows across the coils, or sometimes water flows through them, carrying the heat away from the refrigerant. As the refrigerant loses heat, it cools down enough to condense back into a liquid, but it's still under high pressure. That's latent heat being released. Then this high-pressure liquid flows out through the liquid line.
Okay, so compressor makes a hot vapor, condenser cools it back to high-pressure liquid. What's next? The metering device.
Spot on. The metering device, or expansion valve, or sometimes it's a thin capillary tube, its job is crucial. It restricts the flow of that high-pressure liquid refrigerant as it heads towards the evaporator.
Like a bottleneck.
Sort of, yeah. This restriction causes a big drop in both pressure and temperature. So now you have a cold, low-pressure liquid refrigerant. These devices, like TXVs, also help make sure only vapor goes back to the compressor later, preventing damage. They aim for a state called superheat, meaning all the liquid is definitely boiled off.
Okay, so metering device makes it a cold, low-pressure liquid, and that goes to the evaporator, which must be the part inside the house.
Precisely. The evaporator coil is where the cooling happens for your room. The cold, low-pressure liquid refrigerant flows into these coils. Then a fan blows your warm room air across these cold coils.
Then the air gets cooled down.
Exactly. The refrigerant is much colder than the air, so heat moves from the air into the refrigerant. This absorbed heat makes the refrigerant boil and evaporate back into a low-pressure vapor. This cool vapor then gets sucked back into the compressor through the suction line, and the whole cycle starts over.
Wow, okay. Compressor, condenser, metering device, evaporator. A continuous loop of heat transfer driven by pressure changes and the refrigerant changing state. Makes sense. Now, you mentioned the condenser releasing heat outside. Are there different ways systems do that?
Yeah, several ways to reject that heat. The most common for homes and smaller buildings is air-cooled. Just a fan blowing outdoor air over the condenser coil. Simple, effective.
Okay.
Then you have evaporative condensers. These spray water onto the condenser coils. As the water evaporates, it provides extra cooling, making heat rejection more efficient, especially in dry climates. But you need to be careful with water hygiene, as they can sometimes create aerosols. And there have been links, in some cases, to things like Legionella bacteria if not maintained properly.
Oh, right. Need good maintenance there. Any others?
Well, there's seawater air conditioning, SWAC. Really interesting at coastal locations. You use cold seawater, obviously filtered and treated, to cool the condenser water loop. It can be incredibly energy efficient, potentially saving up to 90% on cooling energy. Great for data centers or universities near the coast, but you have to deal with saltwater corrosion using special materials like stainless steel or titanium.
90% savings. Wow. That's huge.
It can be, in the right setting. And finally, there are larger systems that use water-cooled condensers linked to cooling towers. Water absorbs heat from the condenser, gets pumped up to a cooling tower, sprayed down to cool via evaporation, and then recirculated. These also need careful water treatment.
So quite a few options for getting rid of the heat, each with pros and cons. Okay, let's dive into something we keep touching on, but it's so critical for comfort. Humidity. Why is controlling it so darn important?
Okay, yeah, humidity is key. To really get it, we need to quickly touch on sensible versus latent heat again, remember.
Yeah, sensible changes temperature, latent changes state.
Exactly. Sensible heat is what your thermometer measures when you heat water. Latent heat is the energy used when ice melts at 0 degrees, or water boils into steam at 100 degrees. The temperature doesn't change during the phase change, but a lot of energy is involved. It takes like 540 kilocalories just to turn 1 kilogram of boiling water into steam. That's huge.
Wow. And that relates to refrigerants changing state, too.
Right, precisely. That latent heat exchange is the workhorse of the AC cycle. Now, back to humidity in the room, the amount of water vapor in the air. Controlling it is vital for comfort and for building health.
Why comfort? We said it makes you feel sticky.
Right. High humidity makes it harder for our sweat to evaporate. And since evaporation is our main cooling mechanism, we feel hotter and more uncomfortable even if the actual air temperature isn't that high.
Okay, makes sense. And building health.
High humidity is basically an invitation for mold and mildew growth. Yeah. And it can attract pests too, like dust mites or cockroaches. Not good.
Definitely not good. What are the telltale signs if you have too much moisture inside?
You might see condensation, like fog or droplets, on windows, especially in winter. Damp spots on walls or ceilings, visible mold, obviously.
Yeah.
Peeling paint or wallpaper. In cold climates, ice building up in the attic under the roof. A generally damp or musty smell, especially in basements. Even pipes sweating condensation.
Okay, I've seen some of those. So how do we actually manage humidity levels in our homes?
Well, first, try to limit how much moisture you generate. Use exhaust fans when cooking or showering. Vent that moist air outside.
Good habits.
Ensure good ventilation generally. And insulation is important too. Good insulation, maybe storm windows, keeps indoor surfaces warmer, which makes condensation less likely to form on them.
Right. Stop the cold spots where water can condense. But what if you already have high humidity? That's dehumidifier territory, right? How do they work?
Exactly. If you need to actively remove moisture, you use a dehumidifier. There are two basic types. The most common uses a compressor, like a mini AC.
How does that work?
It draws in humid air and passes it over cold coils. Because cold air can't hold as much moisture, the water vapor condenses out of the air onto the coils and drips into a tank, or gets drained away. The drier air is then usually reheated slightly before being blown back out.
Okay, so it cools the air to squeeze the water out. What's the other type?
The other type uses desiccants. These are materials that naturally attract and hold water molecules. Think of those little silica gel packets you find in packaging.
Ah, right, those things. How does a dehumidifier use them?
Well, a common design is a dry desiccant unit with a rotating wheel. This wheel is coated or filled with desiccant material. As it turns, one part of the wheel passes through the incoming humid air, absorbing moisture.
Okay.
Then that section rotates into another area where hot air is blown through it. This heat forces the desiccant to release the captured moisture, which is then vented out of the unit, often as damp air exhausted outside. The wheel keeps turning, continuously drying the air.
Interesting. So it absorbs and then gets baked dry again. Are there liquid desiccants too?
Yes, there are liquid desiccant systems. These use a hygroscopic a liquid that readily absorbs water vapor, like certain salt solutions or glycols.
How do they work?
Usually there's a conditioner section where the humid air passes over or through the liquid desiccant, and the desiccant absorbs the water vapor. Then, this water-rich desiccant solution is pumped to a regenerator section.
To get the water back out.
Exactly.
Yeah.
In the regenerator, the solution is heated, causing the absorbed water to evaporate off. This water vapor is vented away, and the now concentrated desiccant liquid is cooled and pumped back to the conditioner section to absorb more moisture. It involves pumps, heat exchangers, fans. A bit more complex usually.
Fascinating. Two quite different approaches to grabbing moisture. Now, I saw in the materials a case study looking at adding a separate dehumidifier alongside an existing AC system. What was the thinking there? What are the trade-offs?
Right, that's an interesting question some businesses or homeowners face.
Yeah.
The potential costs identified were things like, the upfront cost of the dehumidifier itself plus installation.
Sure.
Then ongoing costs, extra maintenance, maybe repairs down the line. It takes up physical space, needs managing. Just another piece of kit to worry about.
Okay, the downsides. What about the benefits?
The big potential benefit is saving electricity. If the dehumidifier handles the moisture removal, the main AC doesn't have to work as hard on the latent load. It can focus more on sensible cooling, potentially running less or more efficiently.
Ah, so they specialize.
Kind of, yeah. You also get more precise control over humidity, independent of temperature. This can improve comfort, maybe enhance a business's reputation for providing a good environment, and prevent problems caused by excess humidity.
Makes sense. Any risks?
The study mentioned things like needing the operational skills to manage both systems, the risk of the technology changing, or relying on specific service providers. And financially, it depends heavily on things like electricity costs, how long the machine lasts, inflation, and what kind of return on investment you're looking for. It's a calculation you'd have to do for your specific situation.
Right. It's a detailed cost-benefit analysis, not a simple yes-no. Okay, we've covered mechanics, humidity. Let's circle back to those refrigerants. You defined them earlier. What makes a good refrigerant? What are the ideal properties?
Okay, so the refrigerant is the working fluid doing the phase changes. Not the same as a coolant, which just carries heat without changing state, usually.
Got it.
Ideally, you want good thermodynamic properties. That means it boils at a temperature below your target cooling temp, absorbs a lot of heat when it evaporates. That's high heat of vaporization.
Right.
Has decent density as both a liquid and a gas for efficient pumping. Then, critically, it needs to be non-corrosive to the system components, chemically stable over time, and safe. Safe means non-toxic and non-flammable, ideally.
That sounds like a tough wish list to fill completely.
It often is, and that leads into the history and the environmental issues we touched on.
Yeah, tell us more about that evolution and the problems that cropped up.
Right. Well, the very early refrigerants like sulfur dioxide were effective but toxic. Ammonia, also used early on, is efficient but toxic and flammable. It's still used in big industrial systems with strict safety, but not really residentially. Then came the halomethanes, CFCs like R12, Freon, and later HCFCs like R22. These were amazing, thermodynamically stable, non-toxic, non-flammable. They seemed perfect, used everywhere. Until the 1980s, when scientists realized CFCs were drifting up to the stratosphere and destroying the ozone layer, a huge global environmental crisis.
Right, and HCFCs were a bit better, but still bad.
Yeah, HCFCs deplete the ozone much less, but they are potent greenhouse gases, contributing to global warming. So the Montreal Protocol Treaty led to phasing out CFCs, mostly done by 95 in developed countries, 2010 in others like India and China. And HCFCs are on their way out too, aiming for around 2015, 2020 in developed nations, maybe 2030, 2040 elsewhere.
So a massive shift driven by environmental science. What are we using now then? What are the common types?
It's a mix. We still have some HCFCs being used during the phase out. Then there are HFCs hydrofluorocarbons like R134A, which was common in cars, or R410A in home ACs. They don't deplete ozone,
Good.
but they're strong greenhouse gases. So they're also facing regulations and phase downs now under agreements like the Kigali Amendment.
So the goalposts keep moving towards lower global warming potential.
Exactly. So now we're seeing more use of HFOs, hydrofluorofins, which have low GWP, also hydrocarbons like propane, R290, or isobutane, or 600A, which are very efficient and have near zero GWP, but they are flammable, so require careful system design and handling.
Right, trade-offs again.
And there's growing interest in natural refrigerants like ammonia R717 in certain applications, water R718 in some niche areas, and carbon dioxide, R744, especially in commercial refrigeration and heat pumps. CO2 is non-flammable, non-toxic, zero ozone depletion, tiny GWP, but it operates at very high pressures, which needs different equipment design.
Wow. So the search for that perfect, safe, efficient, and environmentally friendly refrigerant is definitely ongoing.
Absolutely. It's a constant evolution in chemistry and engineering.
I also saw a brief mention of something called adsorption cooling. Is that another alternative approach?
Yeah, it's quite different from the standard vapor compression cycle we've been talking about. Adsorption cooling uses a solid material, an adsorbent, that naturally attracts and holds onto refrigerant molecules on its surface at low pressure. Then you apply heat, maybe waste heat from another process, or solar energy to drive the refrigerant off the adsorbent material at a higher pressure. This higher pressure refrigerant vapor can then be condensed and evaporated like in a normal cycle to provide cooling before being adsorbed back onto the solid material at low pressure to start again.
So it uses heat input to drive the cycle instead of a mechanical compressor.
Largely, yes. You still need pumps, usually, but the main energy input can be low-grade heat. So it has potential for energy savings and using renewable sources in certain applications. It involves components like heat exchangers, the adsorber bed, a condenser, evaporator. It's an interesting technology, though maybe less common currently than vapor compression.
Definitely sounds like something to watch, especially with the focus on sustainability. Okay, wow. We have covered a lot of ground here.
We really have.
From, what actually makes us feel comfortable, that mix of temperature, humidity, air movement, all that.
And how our own bodies interact with it all.
Right. To the nitty-gritty of how ACs work. That whole cycle of compression, condensation, expansion, evaporation.
Different ways to get rid of heat, the crucial role of humidity control, those different dehumidifier types.
And finishing up with the complex world of refrigerants, their history, the environmental challenges, and the ongoing search for better options.
Yeah, it really shows that achieving true indoor comfort is this fascinating balance of physics, engineering, chemistry, and even biology. It's much more than just flipping a switch.
Definitely. So thinking about all this, especially the huge energy use of AC and the environmental impacts we've discussed, it leaves me wondering, how can this deeper understanding help us create living spaces that are, both genuinely comfortable and more sustainable in the future?
That's the key question, isn't it? It seems like it has to be a combination of smarter technology, maybe different ways of designing buildings, but also our own behavior and choices about what comfort really means and how much energy we're willing to use to achieve it. It's a complex path forward, balancing comfort, health, and environmental responsibility. Lots to think about.